AQA Loves Chemistry, June 2022, Paper 1, walkthrough. Question 1. Explain why the first ionization energy of the group 2 elements decreases down the group. Classic question. Explain the trend. Well, the idea that increase in shielding, probably the most logical one, increase in shielding down the group as atoms get larger, hence weaker attraction between the nucleus and outer electron. And all of these type of questions explain why first ionization energy of something decreases or increases. Always about, you need to include about shielding, weak attraction, nucleus, outer electron. You need these specific key terms to get the full 2 marks, 3 marks, or whatever, how many marks it is. Given the equation with magnesium, third ionization of magnesium is measured. So Mg3 plus gaseous plus E minus, and then I've got an arrow there, and that's how it's going to be Mg2 plus gaseous. You just need to know how to construct these. It's just, skill. Question 1.3. Explain why the third ionization of magnesium is much higher than the second ionization energy. Electron is being removed from a subshell which is closer to the nucleus. Electron being removed is less shielded than 3s. Electron is being removed from the subshell which is closer to the nucleus, therefore it's less shielded than 3s. Describe a method to make an accurately known mass solid to beaker to make a solution. 2 marks. Measure the mass of weighing both and solid, add this solid to a beaker, and then reweigh the weighing both and subtract to find the mass of solid added. You just need to know how to do that. It's a practical skills. Then 2.2, the student dissolved this much of citric acid in water, make substitution up to this much, calculate concentration of citric acid in the solution. And first thing I would need to do is find out the moles of citric acid. Then I know moles of concentration of volume, concentration of moles divided by volume. Yeah, that's what I'm going to need to do. So moles of citric acid is the mass, 0.834, divided by the MR, which is just all of that. So 0.834 divided by 12 plus 12 plus 12 plus 12 plus 12, 1, 2, 3, 4, 5, 6 plus 8 plus 16 plus 16 plus 16 plus 16 plus 16 plus 16 plus 16. Then that's the moles. Moles is considered volume. Concentration is the moles divided by the volume. But I want the volume in moles per DM minus cube, not centimeters cube. So I divide the volume by 1,000. So it's 0.500. 8.69 times by 10 to the power minus 3. 8.69 times by 10 to the power minus 3, or 0.00869. 1, 2, 3. Perfect. For each of these 3 steps, identify the mistake, explain why it's a mistake, and then suggest how the mistake can be overcome. So 3 stages is a 6 marker. So I'd say stage 1. What's the problem, or what's the mistake? Well, it says we'll be right with this. Use a measuring cylinder to transfer. No. Use a dropping pipette. Use a pipette. So using a measuring cylinder. Well, explain why it's a mistake. Large uncertainty, hence not accurate enough. Improvement. Use a volumetric pipette or graduate pipette. And yeah, stage 2, another mistake I'm looking for. Mistake. A lot of these mistakes are easy to spot. obviously how it depends how well you know the practical. Slowly add sodium hydroxide into conical flask, drop wires near the endpoint, the indicator just change color, add 5 centimeters cube indicator. It's 5 centimeters cube indicator. No, we don't want to add too much. So mistake, too much indicator may react and affect the endpoint reading. So improvement is that we need to use a smaller volume, 2 to 3 drops, for example. Stage 3, another mistake I'm looking for. Mistake. Now this one's probably going to be the most difficult to find because I've got the using a measuring cylinder, use a pipette instead because of large uncertainty. That was an easy one to spot. The second, stage 2, use too much indicator. That's also not too difficult. But the third one, well, I'm going to talk about. It says rinse a burette with distilled water. Well, that's going to be a mistake as well. So put my thingy there. Rinsing the burette with distilled water. But what will happen is that it will slightly dilute the alkali solution. So improvement is rinse the burette with alkali solution. That's perfectly fine. Complete table 1, use data in table 1 to calculate the mean titer. So just subtracting them. 9505 minus 22.95. The only mistake many students, including myself, would make is not giving it to 2 decimal places. Look at everything else in the table. All of them are to 2 decimal places. So therefore you need to give your titers to 3 decimal places as well. 22.90. Then it says calculate the mean titer. Mean titer is going to be these two then. So 22.90 plus 22.95 divided by 2. $22.925 or 22.93, whatever you want to say. 22.95, 23.10, 22.90, and then 22.93. It says total uncertainty in the use of burette is that calculate percentage in the use of burette in run 1. Now this one's a bit tricky because how do I find the this answer, right? The 22.95. Well, I do my final reading minus start reading, and that's going to be 2 readings. So it's going to be 0.15 times by 2 divided by 22.95 times by 100. Actually, no, it's not. No, it's not. It's not going to be times by 2 because it tells me the total uncertainty is that, right? Okay. If it said uncertainty for one of the readings is 0.15, then I would. But it already tells me it's total, so that's fine. In the A-level papers, they really like to use that trick where you need to then identify as 2 readings, so I need to then times it by 2. But in the AS, they just want you to, it's fine, just substitute your values in. Deduce the bond angles in ASF5, draw the shapes, showing all lone pairs of electrons that influence the shapes. So KRF2 is probably going to be the easier one. It's obviously going to be a linear shape, but it's not asking for that, is it? The number of lone pairs of electrons, well, KR, where's KR? KR is group 0, so it's got full 8 electrons in its outer shell, and it's bonded to 2, so it's going to have 6. So we're going to have 2 lone pairs here, 1 lone pair here, and another lone pair here. Sorry. Then for ASF5, we got AS, which is in group 5, bonded to 5. So F, 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 and then you've got a F here, and it says deduce the bond angle at ASF5. Well, you've got 90 degrees and 120 degrees, and this is trigonal pyramidal. Was it? Yeah, that's trigonal pyramidal, I'm pretty sure. Then it says complete diagram show 1 molecule of ammonia can form a hydrogen bond with a molecule of ethanol. So ammonia, NH3 with a lone pair of electrons, hydrogen partially positive, this is partially negative. And what I want to show really, 1 molecule forms a bond. Well, all I want to show now is obviously the nitrogen, which is delta negative, and then attraction to the lone pair of electrons. And then perfect. 3 marks it up. But you have to be very specific. Include all lone pairs, include the partial charges, include the lone pairs, and then the attraction, like this dotted line basically. Define the term electronegativity, ability of an atom, well, actually, the relative tendency of an atom to attract a pair of electrons in a covalent bond. The relative tendency of an atom to attract a pair of electrons in a covalent bond. Just 2 atoms that form the most polar bond, oxygen and hydrogen, the one with the most electronegative and the one that's least electronegative. Explain why CbR4 is not a polar molecule. CbR4 is completely symmetrical. Molecule is completely symmetrical, hence the dipoles cancel out. Suggestion in terms of intermolecular forces for each compound will explain why CbR4 has a higher boiling point than CHBr3. CbR4 has van der Waals forces between molecules. CHBr3 also has van der Waals. It doesn't have hydrogen bonding. So what else does it have? It has dipole intermolecular forces. Perfect. And how do I know that? Because if you look at CHB3, BR3, it's not completely symmetrical. So the dipoles do not cancel out. Therefore, it is unsymmetrical. Therefore, it does have dipole intermolecular forces. So then I would say for the final mark is that I'll just say the intermolecular forces between CbR4 molecules, because it tells me CbR4 has a high boiling point, so therefore the intermolecular forces between CbR4 molecules are stronger than the intermolecular forces between CHBr3. Question 5. Calculate the mass in kilograms of one of this, and then calculate time taken. So the mass of this, in order to find out the mass of this, I'm going to have to do 121 divided by Avogadro's constant, and then whatever my answer is, then divided by 1000. So 121 divided by 6.022 times by 10 to the power 23, and then divided by 1000. 2.01 times by 10 to the power minus 5 kilograms. And that's the mass of 121 sp plus ion. Now I want to calculate the time taken about 123 sp plus ion. And I've got the mass of it, and I know that it takes this long to do it. So I know K equals that. Need to find out what I need to find out is I need to find out the velocity, and then I can find out the time taken. Perfect. So because if I find out the velocity for 121 sp plus ion, then I can use that to find out the kinetic energy, And once I've got the kinetic energy, then I can use the time taken. Well, the distance times by time, and or velocity is distance divided by time. Time is the distance divided by velocity. Well, once I've got the kinetic energy, then I can work out the velocity of the other ion, and then therefore I can find out the time taken. So I think I'm overcomplicating it, but either way, I should get the correct answer. That's all that matters, really. And obviously, I need to show my working out. So what I'm gonna do first is what am I gonna do first? It's gone through so many steps. I'm gonna find out the velocity. Yeah, that's what I'm gonna do first. Velocity is the distance, 1.05 meters, divided by time, 5.93 times by 10 to the power minus 4. I get velocity as 1.05 divided by 5.93 times by 10 to the power minus 4. 1770. I'm going to leave it like that. 1771 actually. Just round it to that. Then I want to find out the time taken for this, obviously. But now what I can work out is the kinetic energy. And the kinetic energy is going to be the same for both. So it's going to be a half mv squared, well, the mass of this and the velocity squared. So a half my mass, which is 2.01 times by 10 to the power minus 25, a half m and then v 1771 squared, and I get the kinetic energy as 3.15 times by 10 to the power minus 19. Now what I need to do is, now I've got the kinetic energy, I can work out the velocity for the 1 to 3 sp plus sign, because therefore I rearrange the equation, so velocity equals square root of 2ke divided by m. Now m is just going to be the same method I did for the first part, 1 to 3 divided by 6.022 times by 10 to the power 23 divided by 1000, or that times by 1000. So it's just going to be square root of the kinetic energy, but 2 times my answer, divided by the mass, which is 1 to 3 divided by 6.022 times by 10 to the power 23 times by 1000. And I get the velocity, that's the velocity. Then I'm going to use velocity as distance divided by time. Therefore, time is a distance, 1.05 divided by my answer. So 1.05 divided by my answer, 5.98 times by 10 to the power minus 4. Perfect, 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 perfect. Say in terms of electron, the meaning of the term oxidizing agent. Oxidizing agent equals electron acceptor. How many questions left? Okay, not too many questions. Question 8 is just practical skill question, so that's light. And question 7 is equilibrium, so it's just this one really. Oxidizing agent, electron acceptor. Deduce School-Half equation oxidation of iodide ions to iodine, I minus to iodine. So I need a 2 here, plus 2 minus. Choose the half equation show the reduction process in this reaction. Reduction process. The first one is correct. Well, the reduction one, I'm going to go from IO3 minus to I2 then. Yeah, because in this case I'm -1 to 0, so that's oxidation. But in this case, that's going to be +5 to 0, so that's being reduced. Okay, so I need 3 oxygens on the right hand side. So that's 6H pluses. So first things first, I need to add a 2 here. Then I've got 6 oxygens, so I need to add 6H2O. Then I've got 12H pluses, then I add 12H pluses here. Everything balanced. Yes, except for charge, so then I need to add 12H plus 2 minus. That's 10 plus, and then 10E minus. 2 minus RI2 plus 2 minus 2IO3 minus plus 12H plus 10E minus RI2 plus 6H12. Question 6.3. Give an equation to show the reaction between iodine and concentrated ferric acid to form the yellow solid. Identify the foul smelling gas. I already know that one, so let me fill in that. Iodines and concentrated ferric acid. So I've got 6Hi plus H2SO4 to form H2S plus 3I2 plus 3H2O. No, it's not 3H2O, is it? 4H2O. H2SO4 RS plus 3I2. No, this one's a different one. S plus 3I2 plus 4H2O. Hydrogen sulfide is found smelling gas. Or you could say 6H plus 6I minus. Explain how figure 1 shows that forward reaction is exothermic. Well, the forward reaction is exothermic because I know that I increase at a higher temperature, the percentage yield is lower, right? So that's the first thing I would say. Lower yield at high temperature. Lower yield at higher temperature. So what happens at a higher temperature? Well, then equilibrium shifts to the backwards endothermic direction to oppose the increase in temperature. Say with the forward direction results in increase, decrease, and no change in the amount of moles of gas. Where the forward reaction in this equilibrium results in increase, decrease, or no change in amount. What does that even mean? Say whether the forward reaction was going to be the same again. Well, it's going to increase lower yield at high pressure, lower yield at higher pressure, sorry, not high pressure, high pressure. So equilibrium has shifted backwards / to the side with fewest number of moles to oppose the increase in pressure. Sperma using catalyst has no effect on the percentage yield. Catalyst increase the rate of forward reaction and reverse reaction equally, hence no effect. So lower yield at high temperature, which I can see So equilibrium shifts in backwards direction. The endothermic direction opposes the opposing increased temperature. Increases lower yield at higher pressure. Equilibrium shifted backwards to certain fuels with number of moles oppose increase in pressure. And calculus increase the rate of forward and reverse direction equally. Calculate the moles of ammonia present in this equilibrium mixture. And I know Casey's at that much Kelvin. I want to find out moles of this. First thing I would always do is construct the Kc expression. So it's obviously going to be square brackets NH3, because I've got 2 moles of it squared, over hydrogen, which is cubed, times by nitrogen, which is just by itself. It's only got 1 mole. I want to find out ammonia present, so it's going to be NH3 equals the square root of Kc times by hydrogen cubed times by nitrogen. Now I know the equilibrium moles, I know the volume, and obviously the square brackets represents the concentrations. So I'm just going to substitute it on my calculator. Obviously in the exam, show you working, but this is just a walkthrough video on how you do it. So Kc 0.118, and that's the units mole to power minus 2 dm to power 6, times by hydrogen 0.0285 divided by 0.150 cubed times by nitrogen, which is 0.0870 divided by 0.150, and then I get the concentration, and that's the most difficult part, because it's very easy then, once you get your answer, then think that's my final answer, but you need to think about it deeply. Why would I give you 5 marks for just rearranging it and the substitute values? Obviously concentration, that's the concentration. So to find out the moles is going to be the concentration times by the volume. So 0.150 times by that, you're going to get 3.25 times by 10 to the power minus 3. Perfect. Calculate value for the equilibrium constant for this dissociation of ammonia to give hydrogen and nitrogen. So what I can notice from these equations is that they flipped it around, and I've seen a couple of questions like this. Sometimes you need to square root. If they haven't flipped around, yeah, sometimes all they've done is literally square rooted it, so then you square root Kc. But in this case, they flipped it around, so just going to be 1 over my Kc for this, 0.188. The units is going to be 1 over mole to the power minus 2 dm to the power 6. So the units are going to be mole to the power 2 dm to the power minus 6, just the opposite of that, because 1 over, and the Kc value 1 over 0.118, 8.47. And it's very difficult to understand what to do if you've never been exposed to this type of question. That's why for Kc, Kp, Ka, Kw, all of these calculation questions in math, really practice them a lot. All the type of questions they could really ask you about. Identify the gas form in test 1. Effervescence with sodium carbonate. So it's going to be carbon dioxide. Describe further test to confirm the identity of this gas. Bubble the gas through lime water. Lime water turns cloudy. It turns cloudy, perfect. Explain how observation from test 1, test 2 can be used to show that the solution B contains hydrochloric acid. Well, what is sodium carbonate and um, effervescence even mean? It means you've got your H plus ions, right? So what I'd say is that effervescence with sodium carbonate, so it contains H plus ions, or you could say effervescent with sodium carbonate, therefore acidic. But I'd say that, and then white precipitate with silver nitrate, with silver nitrate, in the table, white precipitate acidified silver nitrate. That tells me so contains chloride ions, and therefore, you know, if you've got H plus ions because you've got effervescent with sodium carbonate, and then you've got chloride ions because you've got white precipitate with silver nitrate, therefore it contains HCl. Describe a series of tests the student could use to show that solution C contains ammonium sulfate. Solution C, ammonium sulfate. So what is ammonium sulfate? I've got ammonium ions, NH4 plus, sulfate ions, SO42 minus. So I'm basically doing two tests to show that I've got that. That's all I'm doing. So for the ammonium ions, sodium hydroxide, warm with some sodium hydroxide, damp red litmus paper at the mouth of the tube turns blue, and then for the ammonium sulfate add barium chloride solution, white precipitate formed. And you know what, I should be a bit more specific, add acidified potassium barium chloride solution. Explain how the Montes recorded experiment could use to show that the solution D contains a mixture of halide ions. The second mass is smaller as silver chloride dissolves in dilute ammonia. There you go. And I can show you how it contains a mixture of halide ions because silver chloride dissolves in dilute ammonia. And this question 8, first one, carbon dioxide bubbles gas through lime water, turns lime water cloudy. Second one, well, yes, again, it's about how well do you know your tests. Effervescence with sodium carbonate, so it contains H plus ions. White precipitate with silver nitrate, so it contains chloride ions. Then series of tests, ammonium sulfate, NH4 plus, SO42 minus, warm with sodium hydroxide, damp red litmus paper at the mouth of the tube turns blue. So add acidified barium chloride solution, white precipitate formed. And then this one really is the only, application really that's really difficult in my opinion. The rest of these, how well do you know your tests? And then obviously this one as well. Second mass is smaller because silver chloride dissolves in dilute ammonia, which you need to know as well.